share my screen and make a few comments, just housekeeping comments. First of all, you may find that the homework problems that hopefully you're doing now, the first collection is due Monday. I think that's chapter 1 through 3 I made due Monday. Some of them are going to feel like they don't have a whole lot to do with what we've been discussing in class, and that's because we're at a place where we're about to start calculating some things. The algebra is not going to be too hard, but there are a couple of tools that you're going to see Merman using in his derivations of things to come. One is the Pythagorean theorem, and for some of you, you just may be rusty with that. So there's a homework problem in the homework that's due on Monday that has to do with that light pulse clock where it's at rest, and then we view it again from the point of view where it's moving. And you're asked to use the Pythagorean theorem, and it sort of doesn't really go anywhere in that problem, but it is preparing the way for what we're going to see in chapter 5. So that's for the reading that you're going to do for Monday. You're going to see that exact kind of thing appearing in there. So I was trying to get you up to speed on that if you're not someone who uses the Pythagorean theorem very often. The other thing that's in there are some problems that have to do with just practicing the idea of distance equals speed times time, because that may be something that many of you don't use on a daily basis, but I'm sure that everyone was at one time familiar with it. You've seen me use it in class a little bit, but there are some homework problems that practice with it. So if you're having trouble with those, feel free to ask me after class today, even after class on Monday. If you have to turn in the homework a little bit late, that's fine for this first assignment, although when they're assigned, you really should get going on them because I assigned them at the point where you're ready to start doing them, and that makes it a manageable amount per night. So please ask, and we will find that the homework syncs up more with what we're doing in class, and we're practicing problems during class that are very much like what you're doing on the homework on future assignments. It's just that we haven't really gotten to the punchline yet. And really, Monday is the beginning of the really interesting punchline. Today, we have a technical result that isn't very amazing, as many of you pointed out in your reading responses. Okay, so that's my homework comments. I also sent out an email yesterday that Muchiri reminded me something strange about, or actually it's kind of nice about the Google Sites that I use for our course website. It doesn't require you to continually log yourself in if you're using the same computer. So you can just leave that website up and you'll see the page. You won't have to enter in your credentials probably for another month before it finally forces you to log back in for security reasons. The problem with that is that if you don't reload the page, you won't see any updates that appear on the page. And so you may miss important things. I'm adding things to the website every day. So you really need to, every time you visit that website, just hit the reload button on your browser and it'll bring up the most current version. Otherwise, you might not see things like the slight changes I made to the order of the homework problems earlier in the week and the videos that have been added. Worksheet solutions are being added to the column of interesting solution posts that's sort of in the middle column of the website as they appear. I'm also putting blank versions of the worksheets just in case you want to try them again without the solutions being there, so you can print those out as you want. Yes, just a comment about yesterday. I felt like, wow, without a worksheet to work on, it just didn't feel like I was engaging very well with the class that's here. Now, our numbers have dwindled in the classroom. We're down to 8 here present in the classroom because a couple of people have gone online. And I do feel like we need more sort of breaks from the words and practicing with things. So I'm going to try to make a concerted effort to have you try things on your own. So I've got several worksheet problems that are going to help us think through the logic. The logic today isn't necessarily easy, even though the result isn't very amazing or surprising of the theorem that's being proved in chapter 4. It's especially important for those of you who are zooming in that you have access to that worksheet, and I send it out via email before class starts. So have that at the ready. Even if you don't have a convenient way to print it out at home, you can have it on your screen and then be working on it on scratch paper on the side so that you're with us. That will help us all think through the logic. and also feel more engaged rather than me just talking at you and saying a bunch of things we need to keep in mind, but really working through the logic yourself. I thought I'm going to try very often to begin with a summary of what we've covered so far, because it's easy to lose track of where we're going before we get into the detailed argument in this chapter. So the first two chapters talked about the principle of relativity and the principle of the constancy of the speed of light. And together, these seem absurd or paradoxical, and we've pointed that out of, you know, something traveling fast and then emitting something very fast and imagining what the person on the ground watching all this happen would see. Something I neglected to mention, I probably should have. I don't think Merman mentions it in the book, but the speed of light is a consequence of the fundamental laws of physics that were established at around 1850. It's the laws of electromagnetism that were sort of finalized around 1850 predict that waves, electromagnetic waves, that's not just light waves, but also radar waves and other sort of frequencies, infrared waves and things like that, travel at a certain speed, and it's a definite speed that's predicted. And so right from the point where that prediction was made, the question was, well, what does that mean? There's only one speed. Speed depends on who's looking at it. How could there only be one speed? And that was the beginning of the question of how to think about that. When you think about the speed of light as a consequence of the law of physics, one way we characterized the principle of relativity was the laws of physics are the same in every inertial reference frame. In other words, the laws of physics are one way of characterizing what an experimental outcome would be. And so if you think of the speed of light as being a consequence of the law of physics, PC is just a consequence of the laws of physics, and the principle of relativity says that the laws of physics should be exactly the same in every inertial reference frame. So from that point of view, you can almost just think of, we're asserting the principle of relativity. Every law of physics should be true. And the principle of the constancy of the speed of light was just one of those that appeared around 1850. It's a particularly confusing one, but if we're saying that all the laws of physics are the same in every inertial reference frame, we really kind of only need the principle of relativity. But it's good to remind ourselves and think of the principle of the constancy of speed of light as being something we need to separately rely on, because it's so easy to forget and take for granted that it's not true when it is. So we, in the last chapter, talked about the implicit assumptions about time intervals, lengths, and simultaneity being independent of the inertial reference frame, and that leading to that fallacious proof that the speed of light can't be constant for all observers. If the proof is going to be false, that's what Einstein is asserting, we now have to find out how things like the time intervals between two events, lengths of objects, and whether two events are simultaneous are actually going to depend on who you're asking. Things that are simultaneous, if two firecrackers go off simultaneously at different points in space, that's your perspective. Somebody else is going to disagree with that, and we've got to find out exactly how they're going to disagree. So our goal now is, assuming the principle of relativity and the principle of the constancy of the speed of light, find out exactly how time intervals, that's the subject of chapter 5, lengths, that's the subject of chapters 4 and 6, and simultaneity, chapter 7, must depend on inertial reference frame in order to allow the constancy of the speed of light for all observers in all IRFs. Okay. End of monologue on that, and now let's go into chapter 4. Any questions or other concerns before we begin? Again, I'll remind those of you who are zooming in, just unmute and shout out. I've got the speakers working in the room this time, so we'll hear you loud and clear. I'll do my best to repeat questions that happen in class so that you guys can hear too. Okay, so we're going to prove a result that Merman calls Rule 1. I don't really like Merman's numbering scheme for the rules he's going to prove, because we're going to have rules 1, 2, 3, 4, 5. And you know, after a couple chapters, it's hard to remember what Rule 4 means, or what Rule 4 says, if you're just numbering them like that. So I give it my own name, which is, I'm going to call it Rule L perpendicular, because it has to do with length. when an object is moving perpendicular to its length. So we're going to talk about motion perpendicular to the length of a meter stick. So the rule we're going to prove today, starting with PR and PC, a meter stick moving with a uniform velocity in a direction perpendicular to its length. Well, we don't normally speak that way, but perpendicular to its length. If it's moving perpendicular to its length, that means it's moving in this direction, exactly perpendicular to its length. Has exactly the same length as a meter stick at rest. Wow, that's really amazing. Thanks, Merman, or thanks, Einstein. But this is going to be extremely important for us. We're going to find out that it's actually not true. Oh, and I didn't put that in here, but if you think that's not so amazing, consider the fact that we're going to prove in chapter 6 that if a meter stick is moving parallel to its length, its length changes in a frame where it's moving versus compared to a frame when viewed from a frame where it's at rest. So it's not as trivial after all, and after we prove both those results, we'll be able to talk about moving in any direction, not parallel or perpendicular to its length, but along a direction which is neither parallel nor perpendicular. Something that's absolutely crucial before we start in on the detailed argument. I believe I took this picture from Merman, is that right, of this aquarium? Or is this from somebody else's book? Did you guys see this fish picture? I don't remember where I got it from then. What does it mean to measure the length of an object? Well, of course, we have to measure on some meter stick or ruler where the front of the object is and the rear of the object is. And normally this goes without saying because when we measure something, normally we're measuring something that we put at rest in front of us, right? If I want to measure the length of a book, I just set the book down on the table. I don't try to measure the length of the book while it's zooming by at half the speed of light, right? So we don't have to be very careful about how we do these things. But if something is moving by very quickly, and we're going to talk about the lengths of objects that are moving by really quickly, it's absolutely crucial that we measure the position of the rear of the object and the front of the object on our meter stick at the same time. Look at the picture on the right there of this fish that's moving to the right. If you measure the position of the rear of the fish at an earlier time, and then you wait a little bit and you measure the position of the front of the fish at a later time, you're not getting an accurate characterization of what any normal person would call the length of the fish. The fish in this case isn't this long distance here that's shown on the right. I need to measure the front and the back at the same time. Again, normally we don't think about that because we measure things that we naturally put at rest in front of us. We don't often measure things that are moving by us at great speeds, but this is important to remember. We have to take those measurements at the same time. Second thing I wanted to remind you of is our definition of inertial reference frames, because we're going to be using the principle of relativity today. And it's important to remember that the principle of relativity says what has to be the same between different inertial reference frames and how do different reference frames compare to each other. Well, different reference frames might be going in different directions relative to each other. So that's indicated by these little arrows here. But not only different directions, different inertial reference frames can be rotated with respect to each other. So here I've shown some reference frames where the X, Y, and Z axes of this lattice of meter sticks and clocks that comprises the reference frame might be tilted with respect to each other, maybe even inverted. Like if I compare this one down here to this one up here, this one's sort of upside down. And if I can stop sharing and just draw something for a second. You know, I might say, oh, my particular reference frame from the point of view from which I'm going to observe some events has, for example, what I might call my X and Y axes going like this. And maybe it's, you know, that particular, relative to the room, that particular inertial reference frame is moving with some speed v to the right. That's one way to observe events that are in the room here. We're going to consider a different this particular way of orienting our axes. For example, maybe I take the plus y axis to go down and plus x still going to the right. And it's moving with speed v going to the right. That's not really a rotation, that's really a vertical reflection, but we're still going to consider the change from here to here to be a different inertial reference frame. It's not a very profound change. All we've done is change the direction of the y meter sticks. Plus y was going up, and now it's going down. But when we view things from these different points of view, we're going to see a different view of the world, right? We're going to see a kind of an upside-down view of the world. And so that's a different point of view. And of course, the principle of relativity says the laws of physics should be the same when viewed from those 2 points of view. We just don't normally consider things that are so easily related to each other, so closely related to be different points of view. But those are different IRFs, so they can be rotated with respect to each other. The origins can be in different locations. They can be moving at different velocities. All of those make a different inertial reference frame with respect from one to the other. Okay, let's get into the detailed arguments, and I'm just going to set up several arguments as a series of claims, and you're going to do some of the work on the worksheets proving these claims, or at least going through the logic associated with them. Let's imagine, so we're trying to prove something about a meter stick moving perpendicular to its length. So let's imagine we have 2 identical meter sticks. In other words, we've held these meter sticks here, measured them against each other when they were both sitting at rest. They're absolutely identical. One of them is going to be at rest with respect to observer A, and one of them is going to be at rest with respect to observer B, or inertial reference frame B, which is moving with respect to A. So if we take A's point of view, of course, A's meter stick, A's identical meter stick, is sitting at rest, and we're going to set B's meter stick. Imagine a situation where A sees B's meter stick moving toward A with a velocity, a direction of motion, which is exactly perpendicular to the orientation of B's meter stick in this case, which is parallel to A. Okay, and here's the claim we're trying to prove. First of all, it has 2 parts to it. If from inertial frame A's point of view, stick B moves perpendicular to stick A, and stick B is parallel to stick A, that's as I've drawn it here. The 2 sticks are parallel as observed by A, and stick B is moving perpendicular to its length. Those are the 2 premises. Then 2 things that we want to prove that are a consequence of assuming the principle of relativity. Then from inertial frame B's view, stick A also moves perpendicular to B's length, and stick A and B are parallel. In other words, we're trying to prove something that sounds completely ridiculous to prove, but we're calling into question all of these properties about how lengths and orientations might change as you change perspectives. So we need to be very careful at the beginning. And we're saying if A sees things from the point of view where A's meter stick is at rest on the left, sees things from this point of view, B should see this point of view. Of course, that's what we're expecting, right? That's what Newton would expect too. Okay, but we've got to prove it very carefully. Okay, so the first assumption is that stick A, I really should have said stick A moves in the direction perpendicular to B. No, I did say that correctly. And A and B are parallel. So in other words, well, I'll show you another picture in just a second. It wouldn't be true if from B's, despite the fact that A's point of view looks like this, it wouldn't be true what we're trying to claim here if either from B's point of view, A's stick appeared slanted, or A's stick were not moving exactly perpendicular to B. In other words, A's stick were moving up at an angle. We're going to try to show that neither of those can be true. They would violate the principle of relativity. Again, I know it's not the most exciting sounding result, but that's where we're headed. So I'm going to show things in a color-coded manner, and then we're going to work this out on a worksheet. Okay, so the premise is what was shown on the left in the previous picture, and the conclusion is what was shown on the right, that the 2 sticks are parallel from the other point of view, and the other stick is still moving perpendicular to the first stick's length. So we're going to start with a proof of 1. We're going to try to prove that in the other point of view on the left, stick A moves perpendicular to B. So We're going to prove this by something that's called proving the contrapositive, or proof by contraposition. And if you're not someone, I'm sure the philosophers in the class are familiar with contraposition, but maybe that's something that most people aren't familiar with. One way to prove a result that says, if you assume X, then it follows Y is true, is rather to prove instead that if Y is not true, then X cannot be true. It follows that X is not true. I probably should have made up a simple example of this, but we might say something like, every positive real number has a square root, a real square root. If you take the square root of a negative number, you get an imaginary square root. You may have learned about that in high school. So I'm making that every positive real number has. From this, I claim, in a very trivial sense, 2 has a positive square root. Well, I should have made this up ahead of time. I don't think I like that question. But the idea is we're going to assume that the conclusion is not true, and from that prove that something in the assumptions must not be true. And what we're going to actually show is that if the conclusion is not true, it violates the principle of relativity. And the idea is we want to assume the principle of relativity. So if the conclusion is not true, if that causes us to violate the principle of relativity, then if we're assuming the principle of relativity, the conclusion has to be true. That's the logic of proof by contraposition. Okay? So let's assume that the point of view that we showed on the left, that from A's point of view, here's A in red with A's stick. From that point of view, B's stick is perpendicular to it and moving in the direction perpendicular to A's stick. Let's suppose that 1 is not true. In other words, maybe something like this holds. From B's point of view, here's B's stick sitting at rest, so we're taking the point of view of B, where B is at rest. Maybe we're assuming that stick A does not move perpendicular to B. So maybe stick A is not perpendicular to B, but what we're concentrating on in this part of the proof is perhaps it's true, or let's assume that it's true, that the stick doesn't move perpendicular to B's stick, but rather moves at some odd angle. So we're concentrating on this direction of motion right here. And the idea is we've got to now show that that contradicts the principle of relativity. Somehow, this asymmetry between the two views is going to contradict the principle of relativity. This is not exactly the method. I think Merman really glosses over some things in the proof here, and at least the last time I taught the course, a lot of people called into question Merman's proof, so I developed a proof that I felt was much more airtight. We're going to take a different point of view. We're going to take, and you're going to work out the consequences on your worksheet. I'm instead going to consider some different inertial reference frames. I'm going to say there's an inertial reference frame, we'll call it B prime. And I know these are a little bit light here, but this says B prime. B prime is just like B. B prime is riding along with B, except is viewing things from an upside down, inverted perspective, right? So B just looks at things from the upside down perspective. The same relationship holds between in the inertial frame A prime and A. So A prime view things from an upside down perspective, okay? Let's redraw the left-hand picture from the point of view of A prime and B prime. Well, all you got to do is flip things upside down, and I'm going to have you do that drawing in your head. So what I'm going to do is pass out the worksheet. We're going to work on problem 1 now. And what I want you to do is, instead of drawing things from the point of view, when I say IRFA view, that means the inertial reference frame point of view where that stick A is at rest. So here's A's view. Now we're going to draw it from A prime's point of view, where still this stick is at rest, but we're viewing it from an upside down point of view. And it doesn't seem like a very profound change, but it's going to allow us to prove that the principle of relativity is contradicted. Over here, I'm going to have you draw this is the point of view that where B is seeing it, where B's stick is at rest. Now we want to show the same scene from the point of view where B prime is viewing it, with the only difference that is that B prime is inverted with respect to B. So if you're on Zoom, pull up that worksheet, or if you've printed it out, take out the worksheet, and we are going to do worksheet problem 1 now. There's not a whole lot of calculation. It's mostly a drawing. And then I want you to think carefully. The hard part is thinking carefully about why your drawing, together with the original drawings, shows that there's a violation of the principle of relativity. And therefore, if we assume the conclusion, assume the opposite of the conclusion, and we prove the principle of relativity is violated, then if we assume the principle of relativity, the conclusion has to be true. That sounds a little bit confusing, but if you think about it the right way, it does make sense. So let's take a few minutes and fill out just problem 1 on here. That's going to help us prove part 1 of claim 1. Okay, let me check the rest of the roll here. Yeah, Muchiri's not on there again. Okay, so Camacho, I see you. And Royce. And Joseph, I already got you, and Spencer. So I've got everyone I'm expecting except Muchiri. And for those of you in the class, if you're having trouble getting the point of what we're doing or what you're supposed to be doing right now, let me know. Just raise your hand. I'll come over and help you. Those of you on Zoom, just shout out a question if you're not sure what you're supposed to be doing, and I can try to set it up again verbally. How's it going? Good. Yeah, I mean, if you get the idea, it's not too hard to draw the picture. Putting that conclusion into words, exactly, that's where you have to think about it. Looking good. How's it going here? Yeah, so this looks good when, you know, if this person who's shown sort of faded there views it, of course, that stick's still going to be vertical, and this one's still going to be vertical from their point of view and still moving in that direction, right? Now, if this faded person here, well, let's see. B is saying, at least in this picture, well, I don't really care about the orientation in this case. We're concerned with the direction it's going. It's not moving perpendicular to B in that case. B would say, look, it's sort of moving in the direction towards the top of my head a little bit as it comes toward me, right? What would B prime say in that case, viewing that? Yeah, moving towards my feet. So Plus it's upside down. So when it's upside down, it would actually be tilted the other way. That's not important for this argument. But what is important is that relative to B prime, it's going to be heading down sort of at that opposite angle downward. Looking good. Now the hard part is this down there, figuring out exactly why that's telling us that the principle of relativity is violated. Yeah, looks good. Yeah, so see if you can put into words exactly why those four pictures together might constitute something that contradicts the principle of relativity.
Don't know.
Okay, I see some of you are writing carefully in the last section, trying to put it in words. Some of you have finished your drawings and are thinking hard about what it is that maybe is in there, but maybe we can bring the conversation together now to not spend too much time spinning the wheels. So the idea, again, is that let's suppose what seems absurd to us, and we are going to prove that it's absurd, but we're going to say, let's assume that even though A, whose red meter stick is at rest, sees B moving at A with B's meter stick in this case, in this situation where the stick is perpendicular and the velocity vector, the direction of motion, is perpendicular to A's stick. Despite that, when B views the situation, A's stick is not moving perpendicular to B's stick. If that were the case. And so my suggestion is, let's draw the same picture from the point of view of A prime and B prime, who are just like A and B, except they're viewing the world upside down. And when we draw this from the point of view of B prime, from the point of view of A prime, of course, A prime just sees this stick inverted and this stick inverted, and at least the way I've drawn it, they look exactly the same. So for the comparing the A prime point of view to the A point of view, we would say, look, A prime and A are saying, I'm seeing exactly the same experiment being performed. A prime and A are seeing exactly the same experiment being performed on the left. All I'm doing is inverting the picture and showing it right side up for A prime's point of view. Let's do the same thing for B prime's point of view. When B prime's just sitting there saying, I feel like I'm at rest, let's see what's happening. Well, B saw this meter stick. I don't really care about the orientation right now. We're concerned with the direction of motion in property 1. So B saw this stick. I happen to draw it tilted. But the important thing is the stick is moving upwards toward the top of B's head from B's perspective. If I draw it from B prime's point of view, of course, it just inverts the whole thing. It's almost as it's a mirror image top to bottom. And what that means is B prime, if B sees this meter stick going towards B's head, B prime is going to see the meter stick going towards B's feet. Okay, simple and possibly boring enough. The question is, how does this violate the principle of relativity? Anybody want to try to put it in words? Read.
Well, I said it disregards the principle of the invariance of coincidences. Because, like, they don't, like in the example to the left, they meet at the same place at the same time when they cross each other, but to the right, they don't meet at the same place when they cross each other.
Well, so that might be true if these meter sticks were, or it might not be true what you said if the meter sticks I drew on the right-hand side were actually vertical. Right? In other words, if I happen to have drawn this red stick here vertical and this one vertical, and what I claim is I don't really care about the orientation of the meter stick here. It might be vertical or it might not. What I'm really concerned about is this direction of motion. And if this were vertical, even though it's moving up and to the left, it would cross all points on the meter stick at the same time, right? And it might be such that they cross and they exactly overlap. Who knows? Somebody else want to put it in there. So I'm not sure the principle of invariance of coincidences is necessarily going to help us here. Yes, Jesse. The claim is that, just to restate the comment, that B and B prime should get the same result. In other words, they're performing an experiment and they should get the same result. Why should they get the same result? Just to dig a little bit deeper.
That's the principle of relativity, right? That two observers should get the same result.
Two observers should get the same result as long as the same experiment is being performed, right? And in this, I'm not sure who was talking there, but yes, that's right. As long as you're performing the same exact experiment, two observers should get the same, two observers from different IRF perspectives. If you're performing the same experiment in those IRFs, you should get the same result. Let me just ask you a leading question here. What's the difference between the experiment A sees being performed and the one A prime sees being performed? There is no difference, right? You know, unless you're concerned about the numbering on the meter sticks. Excuse me. If we're just concerned about the orientation and the direction of motion, A and A prime are seeing exactly the same experiment being performed. And that means if the same experiment is being performed in the top and the bottom, then the point of view of the person riding along from the other meter stick should see exactly the same outcome of that experiment. It may be a strange outcome, it may be something we're not familiar with, but if the same experiment is being performed from one person's point of view, we can't have the, you know, in one case, the same experiment is being performed over here, and in one case, the observer sees the stick moving upward towards their head, and in the other case, it moves downward towards their feet in two different inertial reference frames. So the same experiment's being performed, but we're seeing two different outcomes in this case, which would violate the principle of relativity. If the same experiment is being performed in two different cases, then two different IRFs have to see the same result. You can try to put that into words as best. Any other comments on that? And therefore, it contradicts the principle of relativity. This, you know, may seem like an extremely long-winded way to get to this result, but it's important to be very careful here. And as I said, last time I taught the course, several people were not satisfied with Merman's statement of the problem and thought he really does gloss over some problems and uses just principles of symmetry to argue the answer. And it's a fine way to argue. It probably wasn't fleshed out enough in the book. In any case, that violation of the principle of relativity proves then that if we assume the principle of relativity, one has to follow, okay? And that's the proof of one. Now, the proof of two is going to be very similar. I'm going to set it up the same way. Remember, one had to do with the direction in B's point of view, that if it looked like everything was parallel and the direction was perpendicular from the point of A, then from B's point of view, we're now focusing on the sticks being parallel. In other words, we already justified that from the point of view of B, this other stick better be moving perpendicular to B's stick in this case. So I'm not going to draw that velocity vector, the direction of motion, in a wacky direction anymore. I'm drawing it going exactly perpendicular to B's stick over here. But now what we're concerned with is whether these two sticks have to be parallel, which any sensible person would say, yes, they better be. But we're concerned with, could that violate the principle of relativity if they're not parallel? And yes, it does. And we're going to take exactly the same tack. We're going to assume that they're not parallel and show that the principle of relativity is violated. And exactly the same proof is going to go through. So I want to just give you about 2 minutes to think about this. We're again going to consider those upside down observers and draw things from their points of view, try to quickly see that. And now I think the argument maybe can be more easily seen that because the A and A prime are performing the exact same experiment and B prime are related to A and A prime in exactly the same way, we better get the same result from B and B prime. So we're doing problem 2, or worksheet problem 2 now, which is really almost the exact same thing. The drawing just looks slightly different. Okay, I'm hoping not to rush you too much, but since this worksheet 2 is almost the same picture and conclusion argument at the end, I think we can sort of go through this one a little bit more quickly. So again, from A prime's point of view, whose only difference from A is being inverted like that, A prime's point of view looks exactly the same as A's point of view, where they're considering themselves to be at rest. That's how we've drawn the picture. And therefore, A and A prime see the same experiment being performed. And if B prime is related to A prime in the same way that B is related to A, if A and A prime are performing the same experiment, then B and B prime should see the same result coming out of the experiment. But when we draw this from the point of view of B prime, the only thing that changes is the orientation of the stick. B would say that the part of the stick closest to my head is leaned away from me backwards, whereas B prime would say the part of the stick that's closer to my head is closer to me at any point in time than the rear end of the stick, or the farther behind part of the stick. And those are different points of view. So even though we've performed the same experiment over here, and B prime and B are related to A prime and A in the exact same way, B and B prime are seeing different results of the experiment. And therefore, there's a contradiction, and it has to be true that this point of view isn't true. These sticks have to be exactly parallel to the ones that B and B prime are holding right there at rest. It makes something that sounds so simple as a conclusion, I mean, it agrees with our intuition, sound really complicated, but we're trying to be very, very careful of questioning every step, because we're going to very quickly on Monday see some very unintuitive results, and we have to treat them with the exact same care. Okay, just for the purposes of people who are only able to watch online, I have put that proof into words here, and I'm going to hand this out as a piece of paper for the proof of claim 1 part 1 and proof of claim 1 part 2 as a piece of paper to people in class if you want to refer to it. If you're looking at the videos, you're welcome to pause those videos and read through that somewhat long and dense paragraph at the bottom, which puts this into words. But that's what you've essentially argued through in completing worksheets part 1 and 2. I didn't want to send this synopsis out ahead of time for fear you'd read it, and then the worksheet wouldn't have the intended effect.
Professor Kelly, but
Yes.
that would be on the website when you put the solutions for the worksheets, that should be available to us there as well, right?
Absolutely. That's a good idea. I hadn't thought of that yet, but this is another thing I can just put there as a link, and I'll call it the proofs of claim 1 part 1 and 2 from chapter 4.
Thank you.
Thank you. Okay, so you don't have to read through those. Those are putting into words exactly what the argument we went through. Now, that's not what we're trying to prove necessarily. What we're trying to prove is something about the relative lengths of these. So we've just established that the picture that we're supposed to envision now looks like this. So A is riding along with 1 meter stick, and B is riding along with the other identical meter stick, right? And they're moving relative to each other. From A's point of view, A is thinking, I feel like I'm at rest. B is zooming towards me with the meter stick. And if A's view looks like this, what we are now able to conclude is that, consistent with the principle of relativity, B's view has to look completely symmetric. They're still parallel. The other stick is still moving perpendicular to my stick as it sits at rest, okay? Nothing profoundly surprising about that, but we have to be careful about proving things. Here's a second claim, which is easy to prove. If the setup, as we said it before, B's stick is parallel to A's stick and moving perpendicular to the length of A's stick in A's IRF, then there's going to be a time for which A finds the 2 sticks lie on top of each other. And we're going to use that to compare their relative lengths, because if they lie on top of each other, here I'm imagining a situation where maybe their lengths aren't the same when they lie on top of each other. But by getting them to lie on top of each other, I can say, at that instant, if they lie on top of each other, I can check the relative positions of where the shorter one's end appears on the scale of the 1 meter stick, and the shorter one's top appears on the scale of the other meter stick. And we will be sure that we're measuring those 2 positions at the same time, because they're only going to coincide at 1 instant. Okay, and there's not really much of a proof in this case, but in order for that not to be true, somehow this picture in A's inertial reference frame would somehow have to later turn into a picture that looks like this. And that's just simply not what we mean by moving perpendicular to your length. In other words, in this case, if we say this stick is moving in the direction perpendicular to its length, we don't mean that the top is moving faster than the bottom, but that the whole thing is moving as a unit, rigidly perpendicular to its length. So that if they were not overlapping at the same time, that would mean that the top of this meter stick is moving faster than the bottom of the meter stick, and we wouldn't say that it's moving perpendicular to its length. It's partially rotating as it moves as well. So for example, If it's moving perpendicular to its length, what we mean is all points on the meter stick are moving at the same rate perpendicular. So when the bottom moves 0.3 meters, the top moves 0.3 meters, and they line up. They're going to coincide. I didn't draw them right on top of each other because they'd be kind of hard to see, but imagine that they're exactly on top of each other at this time. Okay, that was claim 2. Just to be a little bit careful, make sure that there is an assumption that's going on there, but the words moving perpendicular to its length, we got to understand that that means the whole meter stick is moving rigidly, not rotating, and in the direction perpendicular to its length. So all points on it are moving at the same speed. Claim 3 is the one we're really here to prove. Assume the principle of relativity and the sticks A and B are identical when compared when they're both at rest. So there's nothing different about these sticks whatsoever. If B's stick is parallel to A's stick and is moving perpendicular to its length in A's inertial reference frame, then the thing we want to prove, the whole point of this chapter, is that B's stick and A's stick will have the same length as measured in that inertial reference frame where A's stick is at rest and B's stick is moving. In other words, when things are moving relative to you, they don't change length compared to how they are when they're at rest. Okay, so let's develop the proof for this. And I'm going to start it out, and you're going to finish it out in problem 3 on here. Again, we're going to assume the opposite of the conclusion that we want to prove, and we're going to prove that that's in contradiction with the principle of something that we assumed at the top, the principle of relativity in this case. So we're going to show a contradiction with the principle of relativity. And we're going to do that by developing statements that the different observer A, which is at rest with respect to stick A, and observer B that's at rest with respect to stick B are going to make. So looking at the situation on the left, A would say stick B is moving, and it's shorter than stick A when stick A is at rest when B is moving by. In other words, well, I sort of set this up in a very particular way on the worksheet problem 3. I'm just going by the picture that's shown here. Suppose that this is the picture that A sees. Here it is at an earlier time as seen by A. Here it is at a later time when they're coinciding, and we're going to use that coinciding. Suppose that A says, of course, stick B is moving in the way we said, and it's shorter than stick A, which is sitting at rest. So when it comes by, the top end of stick B passes below the top end of stick A, and the bottom end of stick B happens to pass above the bottom end of stick A. Okay? So stick B is moving, and it's shorter than stick A at rest. It's moving in the particular way we've said. I didn't want to say that all over again. Let's just imagine a particular situation. I think this is exactly the one considered in Merman, if I remember correctly. Suppose A makes the statement. What this means is the 95 centimeter mark on stick A lines up with the 100 centimeter mark on stick B. Stick B is shorter, so maybe this is its 100 centimeter mark here if we have the high end of the scale at the top, right? This is the 100 centimeter mark on stick B as it's moving by. It aligns when these two coincide with the 95 centimeter mark on stick A. Let's just imagine that that's the case. And also, let's imagine A observes. So both of these are A statements. That's what I mean by the A colon. This is something A is going to declare to be true. Also, my 5 centimeter mark aligns with B's 0 centimeter mark. So here's B's 0 centimeter mark down here, and here's A's 5 centimeter mark, which isn't quite at the end. Okay, that's my evidence that B's stick is shorter. Look, I measured them at the same time because they only coincided for an instant. That's a true measure of length. And the ends of B's meter sticks line up with marks that are not quite at the ends of my meter sticks. So B's has shrunken. We're now going to consider what B would say using the principle of invariance of coincidences, because we've got some coincidences happening. The 95 centimeter and 100 centimeter marks on the 2 meter sticks aligning is a coincidence, and it has to be the same coincidence from the point of view of B. We've stated it from the point of view of A, but now we're going to use the fact that B is going to make the same statement. So try worksheet problem 3. I'm sort of leading you through what kinds of statements B would make about this situation, given that the 2 meter sticks align at some instant. And again, if anybody is confused about what they're supposed to be doing, or just confused about the way this is set up on the worksheet, either raise your hand in the room or shout out on Zoom, and I'll try to state it again or in a different way. Okay, I'm going to give us one more minute, and in the interests of making sure people are following along, I'm going to ask some people for what they filled in on A, B, C, D, and E. That includes some of you Zoom folks, so if you have any questions about how to interpret what's on there, ask now. Okay, let's finish up together. It looks like most in the room are sitting and waiting. Spencer on Zoom, if you're there with us, can you help me think about what, I'm looking at question part A, what statement will B make about which stick A markings and which stick B markings align, similar to the statement of A just above? How would B state it?
Okay, so B would within their IRF, their 0 centimeter mark would line up with, well, I don't know, I'm getting kind of like confused and thinking about this, but it would think A is bigger, correct? But it would be by the same rate, just kind of opposite.
Yeah, so the statement that's being asked for is what markings on meter sticks would align. So A is saying, I see my 95 centimeter mark align with your 100 centimeter mark on B as B goes by. Now we're taking the point of view of B, and what is B going to say about the 95 centimeter mark and the 100 centimeter marks? Do they still align from B's point of view? And if so, why?
Yes.
I agree, yes. What would be the justification for that? There's a name for how we justify that.
Okay, so it's the simultaneous occurrence.
Yeah, it's something like that. I agree. It's hard to remember that name. I don't want to give another acronym to it, but it's the principle of invariance of coincidences, which means that if two things sort of align in one IRF at a particular point in space at a particular time, they have to align in all IRFs. Otherwise, you can imagine situations where there would just be logical contradictions. Different things happen in different IRFs, like two cars collide in one IRF, but they miss each other in another IRF. And those people who observe those could come back together and compare notes and say, well, either one happened or the other. Let's look at the wreckage and see which one happened. So if that isn't true, we've got serious logical consistency problems with our theory. So we're going to assume that that's always true. And so B has to exactly agree with this statement of A here. When B looks at it, from B's point of view, the 95 and 100 centimeter marks on the respective sticks align exactly the same way they did as observed by A. And the same thing for the 5 and the 0 centimeter marks aligning. That's a consequence of the principle of invariance of coincidence. Yes, you stated it in a different way that sounds exactly like what the content of that is. It's a mouthful. Okay? And most importantly, you know, again, we decided that in either point of view, because now both the sticks are parallel and moving perpendicular to the length of the other one, they're going to overlap at the same time. And so therefore, if they only overlap for that instant, those two events of the alignment happen simultaneously. So we're really measuring something that's going to allow us to conclude about the length of a meter stick. Thank you, Spencer. Let's have someone in the room go on to the next one, which is part B here. What statement will B make about the stick, which stick is shorter? Jack just said stick B must be shorter, right? Because look, B's end lines up with somewhere in from the end on both sides, right? B stick markings line up with a point that's somewhere not at the end. The end of B's stick aligns with markings that are not at the end on both sides of A's stick. That must mean that stick A is, oh, I guess I'm jumping ahead here and giving the answer to C. Stick B is shorter. I mean, that's just because the way they line up, right? B is just sitting there. The stick seems totally normal to B, and therefore A stick appears to be longer from this point of view, right? Because these are normal meter sticks. When you're sitting with them at rest, they've got to behave in the normal way. So both A and B see their meter stick as being normal. A's stick, from B's point of view, seems to be longer than B's stick, and therefore A's stick has the problem here. And this is really the answer to C here. What statement will B make about the relative length of stick A while it moves past? Stick A is moving, and it's longer than stick B at rest. And therefore, if we were to restate that generically in terms of what happens to meter sticks moving perpendicular to their length, B would say the moving meter stick expands along its length, whereas A would say in exactly the same situation, the moving meter stick contracts along its length. So I'm comparing what B would say in part D to the statement that A made at the very top of this list of statements. A says B's stick is moving and it's shorter than the one at rest. B says A's stick is moving and it's longer than the one at rest, and they're identical sticks, and they're both moving in the same way. We worked very hard to establish that they were both parallel and moving perpendicular to their length. So they're performing exactly the same experiment. We're just checking it from different points of view. Okay, and that contradicts the principle of relativity. We're performing the same experiment, sending a meter stick towards us, parallel to our meter stick and moving perpendicular to its length. One IRF says it shrinks, the other one says it expands. They've got to have the same outcome of the experiment because we're performing exactly the same experiment. But if this were true, the principle of relativity would be violated. And therefore, if we're assuming the principle of relativity, this cannot be true. In other words, one can't be shorter and one can't be longer. They have to be exactly the same length. And so this, again, is the sort of really unexciting result. It agrees with our Newtonian and everyday intuition that Merman calls it Rule 1. I'm going to call it Rule L perpendicular because it's about lengths of things moving perpendicular, meter sticks moving perpendicular to their length. A meter stick moving with uniform velocity in a direction perpendicular to its length has the same length as a meter stick at rest. You can kind of phrase this two different ways. You can phrase it in terms of two identical meter sticks. One's moving and we're comparing it to one that's at rest. Or we can think of a single meter stick and we can view it from the point of view where we're sitting at rest with respect to it, and then view it again when we move with respect to it. There's only a single meter stick. It's really the same thing as long as you assume the meter sticks are identical in the first case. In any case, there's no effect. Our intuition guides us correctly here. This is the last time in the course that this is going to be true. But it's actually pretty interesting because it's going to allow us to conclude exactly the way generic shapes deform when we measure their dimensions and they're moving relative to us. We're not always going to be concerned about meter sticks. We may be concerned about a spaceship with a weird shape. And if it's moving past us with the front end in front and the back end behind, we want to know exactly how it deforms. And what this result is telling us is, well, it's not going to deform at all along the direction perpendicular to the direction it's moving. All bets are off along the direction it's moving, but along the direction perpendicular to which it's moving. And let me just stop sharing for a second so I can draw on the board. So suppose here's what a spaceship looks like when it's at rest. I'm just going to draw it as a big bullet like that. Oh, okay, we'll put some fins on it. Why not? There we go. There's our spaceship when we're just sitting at rest with respect to it. Now, either we can send the spaceship moving fast relative to us, or I might move fast past it and observe it and make careful length measurements. But we have to be careful to make those measurements at exactly the same time from the point of view of the person who's doing the measuring. And what we found out is that it shouldn't shrink at all along this direction. This dimension is always going to be the same, whether it's at rest or moving by at a high speed. Same with this dimension. That's not going to change, because I could have aligned up a meter stick there and had it moving in that direction. So this dimension is not going to change. This dimension is not going to change, and so on. What we don't know is about these perpendicular dimensions, and we're going to find out about that in Chapter 5, and maybe some of you have heard about this. It actually contracts along that direction. So this whole thing, if I could try to draw what the result of after Chapter 5 would be, is this thing gets compressed along the direction when it's moving in this direction at a very high speed, velocity v or speed v that's very close to c, half of c, 3/4, 0.99. It becomes more and more compressed along this direction, but along this direction, it doesn't get compressed at all. Not sure if I'm doing an exact way, but you know, this looks like it's compressed by about a factor of half along the horizontal dimension, but not compressed at all along the vertical dimension. So this is an important part of the way things get deformed when we measure their dimensions as they're going past us at high speeds. The other half will be, well, we'll have to see. We're going to spend a couple of days on chapter 5 because there's a substantial amount. It's not a short one like this. There's actually a substantial amount to be thought about in there. So we'll probably spend Monday and Tuesday on that. Okay, any questions? I think I have some reading responses just to throw in the last few minutes of class. Jack? So the question is, this rocket can only be moving past you in the direction perpendicular to the vertical direction in the picture at one instant? Yes. So I think you're saying, here's an observer. Here's me. I'm going to draw myself as just an eye looking up in that direction. Here's me looking right here. Yes. And so at one point, the tip of it would be right above my eye, and in another point in time, very short after that, the middle of it would be above my eye, and then at another point, the tail would be above my eye, and so on. And that would all happen really fast if this were, you know, 0.99 C or something like that. Okay, continue the question, or? Let me unshare this so the other folks can see this. The important thing is, where I thought you were going to go with it is, yes, it's true. One observer is only going to be at one particular point on here. And so one observer can't simultaneously measure the position of this end and this end to conclude the length because they're at different positions. Now, they may only be 10 meters apart, but still, we want to be very careful and make sure that we don't have to wait for the time that that signal takes to get to us if we're relying on a visual clue from it or something like that. So instead, you know, suppose I'm in inertial reference frame A. We're going to assume that A not only has an observer here, but A has an observer over here, and here, and here, and here, and other ones up here too if we need them, right? They're going to be everywhere in space. And they all have clocks that are synchronized. So everyone in inertial reference frame A is going to have a clock with them that's synchronized. And they're going to say, right at noon, I want you to, whoever's closest to the end, the back end of the ship, you measure where it is on our meter sticks. And whoever's closest to the front of the ship at noon, tell us where on our meter sticks the front end is. And then we can take the difference between those and figure out what the length of the ship was. So it's, even though we're talking about it as if there's only one person's point of view, we're really imagining that there's a whole collection of observers that are really sitting at rest with respect to us. We all have synchronized clocks, so we know we can do something at the same time from our point of view and make measurements that way. We'll get more into that on Tuesday. Monday's result is probably even more befuddling than this. Let me just finish with a couple reading response things again. Any other comments before we finish up with a last few here? Most of you commented that, hey, this chapter was easy and it agrees with my intuition, so no problem. Even though the technicalities, if you really want to be careful, it's tough to check everything at every level like we did working through it in this class. It seems to imply that if you had a meter stick that was spinning as it was moving in a constant direction, it would be constantly changing its length. And yes, if you already understand the idea that things, if we have a meter stick that is spinning as it moves by us very rapidly, it would always be shrunken along the direction that its center is moving and not shrunken along the direction that it's not moving. Or another way to say the same thing is if someone rides a bicycle by you at very close to the speed of light, the wheels would be shrunken along the direction they're moving, but not shrunken along the perpendicular direction. So they would appear to be, if you could measure it carefully, they would be oval shapes or ellipse shapes for wheels rather than circular shapes, even though from the point of view of the person on the bicycle, they're just perfectly normal circular wheels. So yes, if you have a meter stick that's spinning while it moves past you really quickly, it's going to change length. It's going to get longer and shorter, as assessed by you, not as assessed by someone who's riding along with the meter stick. By stating the importance of the perpendicular motion, we can only be led to believe that a non-perpendicular movement is going to change the length of the stick. I don't see how this is possible, considering then you would violate relativity. Well, we're going to see how it's possible. It does. The important thing right now is that it seems like it is impossible. That's what makes relativity so interesting, is that it conflicts directly with our intuition, and it seems like it's impossible. It's not impossible, but we have to very carefully say how a lot of things change at the same time. I doubt sticks will ever change length. If they ever change length, it would violate relativity, because you would simply look outside and see that everything at rest with you is larger than it should have been. I'm not sure this even violates it, though. If I look out at something moving, I can tell I am moving. Yes, if you look out the window and see something that you're moving by, you can tell that you're moving. But that's not what the principle of relativity is telling us it's not possible to do. It certainly is true that if I zoom by the sun and I look out the window of my spaceship, I will see the sun moving by me, and my correct conclusion is I'm moving relative to the sun. That doesn't violate the principle of relativity. That just means it's possible to tell your motion relative to something else. Principle of relativity says, well, if I move relative and I see the sun zooming by me, and then I take me and the sun and speed them both up and look at it, and something different happens in an experiment while I'm doing that. I take everything that I'm observing and interacting with and speed them up, throw them at, accelerate them to a greater speed, and perform the same experiment, and your coffee boils at a different temperature or whatever might happen differently then. That would violate the principle of relativity. But yes, this logic is confusing. They will, in fact, change length. But it's a little bit confusing, because the definition of length depends on measuring things, the two ends, at the same time. And we're going to find out that there's something really peculiar about that, because people disagree about what at the same time means. Things that happen at the same time in one reference frame are going to be judged to be non-simultaneous in another reference frame. That's something that is a little bit confusing. It looks like I pasted the same thing twice in here, so that's the end of it for today. So, as always, stay after if you want help on homework or anything else. So that's the same for you Zoom folks. Otherwise, I'll see you in the forum today. I'm greatly looking forward to that, our first forum of the term in Dr. Kadavid's class. Jack, I was going to say to you and Everett, both of you were making interesting objections or possible contradictions with the idea of clocks slowing down as you move, and what would happen if, Jack, yours was if I went far away and then came back, and what would happen to the clock on the wall. Everett was imagining a video feed that would show him exactly what was happening on the clock back at Earth while he were speeding away, or vice versa, maybe to people on the Earth watching the one on the spaceship. All of those are going to come together in something called the twin paradox, and we're going to be doing presentations, as I mentioned on the first day, on paradoxes. And one of the things you guys might consider doing is developing that into a talk where you can explain that. We will give sort of an explanation of the twin paradox at one level, but you'll find that explanation only raises further questions which are going to get at what you guys asked. It's not the first explanation that shows things aren't contradictory that satisfies your questions about, well, what happens if we ask someone who was right there? What did that clock read at that time? Those kinds of things are things you might tease out. So keep thinking about that. And we don't have all the tools where we can answer those questions yet, but we will pretty much after chapter 7. So it's something to keep in mind. See you in a bit on camera.